So today we are going to start the third chapter. So the first two chapters in the book, they mention it is actually related to data collection. And all the remaining chapters they have considered under something descriptive statistics actually. So this book doesn't actually contain inferential statistics, right? Even though some topics like regression analysis and some other things are generally inferential part, the book contains discusses only the descriptive part of that thing. Right? So here I sometimes find a very surprising why they have chosen this particular topic here. Right? Histograms cannot be a meaningful topic for this chapter because they talk about so many other things also. But anyway, I think mainly they talk about the histogram and uses of histogram, applications of histogram and so on. So histogram, what is histogram? Histogram is actually a graphical display of data. It's a way of, one way of summarizing data. Right? In a way, histogram is similar to something called bar chart, you already seen. But there are some distinct differences between bar chart and histogram. So in order to discuss about these differences and so on, so it says here the histogram is a graphical display of the distribution of quantitative variable, mainly when the variable is continuous. But it may also be used for discrete variables with many distinct values. Right? So in order to understand this expression, first of all we have to understand several words here. Right? Call it quantitative variable, distribution, continuous, discrete variables, and so on, new words. So I thought so in here the order I have changed. The book, it's not the same order as in the book, right? So I thought, because of this expression here, I thought we should discuss about these things first. Different things about the data, variables, different types of variables and so on first, and then I'll come to the histogram. Right. So before we proceed with histogram, let us briefly review the classification of variables and data, right, in order to clarify the previous expression. So what are variables and what are data? When you talk about the variables, you already know what variables are mathematically, right? For example, if you say x equal to y is equal to 2x plus 3, you call y is a variable, x is a variable, right? So that's a mathematical variable. Right? They are usually, you assign some value for x and then find out the value of y. We assign the values, right? For a given value of x, we can find out y. And usually these relationships are deterministic, right? In relation, x and y, mathematical relationships are mostly deterministic. In statistics, however, a variable is some characteristic which varies from unit to unit or person to person. A unit can be a person, or maybe a patient. I have given some examples here. Right. The household itself can be a unit from which we get some information. Right. So a family like that. So a variable is some characteristic of a unit which varies from unit to unit, right, in statistics. So therefore in statistics we don't assign values. Right. They naturally have values. Right. For example, if you take a person, a variable is say height of a person. Right. So height varies from person to person. We don't assign the height, no. The person naturally has some value. Right. So that is the difference between in mathematics and statistics, the idea of variable. In mathematics, variables are we assign the values for variables. In statistics, they also vary. In both cases they vary, values can be varied, but Naturally, statistics variables have values already. So those values that they naturally have are called data actually. So in order to get the data, we have to use a proper method like observation or questioning, that kind of things. We can obtain the data. Right. So the observed outcomes in statistics are called data. They can be mainly in two forms. Right? Sometimes the answers or what we observe or we record can be a number. So in that case, we have a numerical observation. Or it can be some other thing like a grade, right? A, B, C, D. It's not a number, right? In a question whether you are male or female, the answer male or female. So that's not a number, right? So in that case, the data are qualitative. Right, so therefore, mainly there are two types of data, but nowadays we have different types due to big data. But as far as statistics is concerned, mainly these two are the types: new numbers and not numbers. Numerical data are also called quantitative data. Numerical ones are called quantitative. The other ones, categorical ones, are called qualitative. So here are a few examples. Variable can be the blood group, right? So that is the characteristic that we observe. So from person to person, the answer, if I ask what is your blood group, answer is different. So these are the possible groups, right? These are the possible groups. So the data can be A, B, also. And if you look at the variable age, age again can be defined. You have, when you ask a question to get data, usually you have to be very precise. For example, if I ask what is your age, you don't know what to give actually as the answer, right? Do you want, maybe you will ask, do you want my age today? Or do you want my age at the last birthday? Or do you want my age at the next birthday? What? So it has to be very clear, right? So if I say, what is your age at your last birthday, then it's going to be an integer, full number, right? Full number, right? So the data can be like 18, 19, 20, 21 and so on. Only full numbers. But if you just say age, you can express age as a decimal number if you want, right? As of today, for example, right? It can be a decimal number. So depending on the question, how you define the variable, the type of the data going to be depending on that, and based on that, later on we can further classify these variables into different types. Right? So if I consider the customer satisfaction, right, in a supermarket, for example, if I ask how much satisfied you are about the services. So in that case, data are going to be something like this. We can put satisfied, neutral, or dissatisfied, or maybe you can have more groups, but they are qualitative. Right? Monthly income. Right? So monthly income also can, you have, when you ask the question, you have to be careful sometimes. Do you want it approximately to nearest 1,000, for example? So in that case, answers will be something like that, or it may be nearest 500, nearest 100, the way that you ask the question has to be clear. Or you may be filling a questionnaire where there are categories given for income. Right? So if your variable is monthly income and the data are like these numbers, then in that case the variable is quantitative. If you are looking at the variable monthly income, but the possible data are groups like this, then still the variable is monthly income, but now it is a qualitative variable. Because these are not, even though these are numbers, this is one group, this is one category, this is another category. It's not a single number. Right? So these data they are going to be categorical. When I select, for example, if my income is in this group, so I am in that category. So my data are categorical, not numerical in that case. So you can see that the way that you collect the data is important to decide whether the variable is quantitative or qualitative or numerical or categorical. So in this case, this is blood group is a qualitative or categorical variable. Age is a numerical or quantitative variable. This customer satisfaction is a categorical variable, right, or qualitative variable. Monthly income here is numerical or quantitative. Here it is categorical or qualitative. So I have another one variable called height. So height again are going to be numerical, right? It may be in centimeters. So you can again ask to the nearest centimeter or nearest millimeter or whatever. Data are going to be numerical. So therefore, variables, as I mentioned, can be first divided into two groups: qualitative or quantitative. Qualitative, in their case, the data are categories. Variable is quantitative if the data are numbers. In numbers, when you say numbers, they have to be real numbers, right? For example, in the income group, I had groups made up of numbers, but they are not now real numbers. They are only categories. Even for example, if I ask the gender, and if I ask them to record it as 1 and 0 or 1 and 2, for example, male for 1, female. So now the data are numbers in that case, but the gender is not a numerical variable because those numbers are not real numbers. They are just labels in that case. So in that sense, if the numbers are real numbers, then variable is quantitative, otherwise it's qualitative. Now these variables you can divide again into two groups, and these ones can divide into two groups. So qualitative data, mainly we can divide it into two groups depending on all the qualitative data have categories, right? Their data are categories. So sometimes these categories have a natural load. Sometimes there is no order. For example, you cannot say one category is better than the other category or bigger than the other category. If you can say like that, then we say there is an order. But otherwise, there is no order. For example, if you consider the gender as a variable, that is a qualitative variable. The two possible categories are male and female. So there is no general consensus that males are better than females or females are better than males or any other order is not there. So therefore, that type of variables are called nominal variables. It's a categorical nominal. Right? No order between the categories. On the other hand, if there is an order, for example, subject grade A, B, C, D, and so on, we know that A's are higher than B, B's are higher than C, always that is naturally normally accepted order. So like that, if there is a normally accepted order, then that kind of variable is called ordinal variable. Right. Now even though there is an order, right, one is bigger than the other one or better than the other one, the differences doesn't have any meaning. Difference between two categories, for example, doesn't have a meaning. What is the difference between A and B? If one has grade A, another has grade B, we cannot talk about the difference. Difference doesn't have a meaning in that case. We know only that one is bigger or better, that's all. And then qualitative variables we can divide again into two types depending on the type of data. Discrete and continuous. A variable, quantitative variable is called discrete if the set of possible values for that variable, set of possible values, is a countable set. It's countable. That's the actual definition of discrete variable. Many people think that discrete variable means a variable which can take integer values. That is not really correct. Most of the times it's like that actually. Discrete variables take only integer values. For example, if you say number of children in a family, so that is a variable. Number of children in a family vary from family to family. Number of children can be 0. The next possible value is 1. Next possible value is 2. Next possible value is 3. Like that. So in that case, the possible values are a set of integers. And in addition to that, it is actually countable. We can count these numbers separately. This is the first value, this is the second possible value, this is the third possible value, and so on, countable. So that variable is actually discrete because the set is countable, not because the possible values are integers. On the other hand, if the set of possible values are is not countable, then we call that variable continuous. For example, if you consider the height of a person as the variable, the actual height, here we are not talking about what we record, because what we record is always going to be up to a certain decimal numbers. That's all we can do using whatever the measurement instrument we have. Right? So the data may look like, for example, if you consider the height, right? If you say in centimeters, 100 centimeters, and then maybe 101 centimeters. If you measure whatever the tape can measure only up to 1 centimeter, right? If you cannot measure more accurate than that, then the possible values will be integers. Right? But actual height doesn't have to be that value. No, there is actual value. So the set of all possible values, not the observed values, the possible values, is not countable in that case. Right? It can be anything between some two values like 4 feet and 7 feet or whatever. It can be anything between those. So in that case, the set of possible values is not countable. So it is a continuous variable. So here I have mentioned that because many people make that understanding wrongly, especially the discrete data. I have seen even in the books, when the data are full numbers, we say that's discrete. That's not the definition. Of course, when the data are full numbers, they are, if the actual possible values are only full numbers, then it is discrete. But it is discrete not because of that, it is discrete if the set is countable. Right? So in practice, the data of numerical variables are always discrete because we use some kind of measurement device that is accurate up to a certain level only. So therefore, for example, even if the data have decimal numbers, if you can measure something height up to millimeters, right? So then there will be decimal numbers. If you record the data in centimeters, there will be decimals. But still, up to maybe 1 decimal or 2 decimal, right? So then the data look like discrete, right? But actually there are several other values possible, but we cannot get those things accurately because we don't have proper suitable measuring device for them. Right? So in practice, the data of numerical variables are always discrete because every measurement is taken with limited accuracy. However, the variable itself may be continuous, since in theory it can take any value in an interval. Right? So when you decide whether it is discrete or continuous, what you should look at, first of all, the possible values, actually possible values, whether the set of possible values is discrete or not discrete. So height of a person is continuous in that sense. Number of children in a family is discrete. So I have given here a few examples for which, and sometimes other people also think, sometimes people understand that the discrete variables, the set of possible values, always have the same gap. Right? For example, if you consider the number of children in a family, of course that is correct. Right? Possible values are 0, and the next possible value is 1, next possible value is 2. So the gap is always between 0 and 1, and 1 and 2 is 1. But it doesn't have to be like that for a discrete variable always. So that property is not a property of a discrete variable, defining the property, even though that property exists in discrete variables sometimes. So I have given some examples where the gaps are not the same, but the variable is discrete. So denomination of, for example, currency notes in Sri Lanka, right? If you look at the possible values at the moment, 20, 50, 100, 500, 1000 and 5000, right? So the gaps are not the same, but these are integers in this case. So the variable, this variable is therefore a discrete variable. It's a discrete variable. Set of possible values. It's countable. Right? The first possible value, second, third, fourth, fifth, and sixth. It's countable. Right. And if you consider, for example, bus fare in rupees. So bus fares are like this. Again, the gaps are not the same. Right? There are only some distinct values. So this is a discrete set. Right? Even though some people think that the discrete values cannot take decimal points. No, it's not like that. Here we have kind of decimal points, but still this set is a countable set. So therefore the variable is discrete. No, gaps are not the same. Decimal numbers are possible. And if you look at the, for example, if you define a mathematical variable like proportion of students, proportion of male students in a sample, right? If you randomly select a sample of students, say 10 students, then you find out the proportion of male students. Right? So the number of male students can be 0, 1, 2, 3 up to 10. So therefore the proportion can be 0 divided by 10, 1 divided by 10, 2 divided by 10, 3 divided by 10 and so on. So those are the possible values for the proportion of male students. Right? So they are not full numbers, they are decimals. Just because it is decimal, it doesn't have to be continuous. Right? The set of possible values here is a set of a countable set. So therefore the proportion is a discrete variable in this case. Of course, if the sample size was 1 million, right, then the possible values are going to be very, very close now. 0 divided by million, 1 divided by million, 2 divided by million, 3 divided by million and so on. Those are the possible values. Still, theoretically, the set is countable. Right? So theoretically it is discrete, but sometimes in the analysis we consider it as approximately continuous, because the gaps are very, very, very small in that case. So we can use sometimes the methods that is suitable for continuous variables can also be used to analyze that kind of data in that situation. Right? So these are important distinctions. One thing is the classification is important mainly because when you go to analyze data, the available techniques for analyzing data depends on the type of data. Right? The methods that you use to analyze quantitative and nominal data is not the same as the methods that you use to analyze, qualitative and nominal data are not the same as. Probably you have better methods to analyze qualitative and ordinal data, right? More powerful methods. Right? So in that case, you don't, if your data are qualitative and ordinal, you should not use a method that is suitable only for qualitative and nominal data. That method may be less powerful in that situation. So therefore, first of all, we have to identify, before even we look at what to do or analyze the data, we have to first understand the type of data, type of variable and type of data we have. Okay, just let's go through this very simple activity. Tell me each of these gives you a variable. Tell me whether these are first of all qualitative or quantitative. If it is qualitative, tell me whether it is nominal or ordinal. If it is quantitative, tell me whether it is discrete or continuous. Number of students in a class.
Quantitative.
Quantitative.
Discrete.
Employment status, if you record it as this: employed, self-employed, unemployed.
Qualitative.
Qualitative.
Nominal. Nominal.
Nominal. Why do you say it's nominal? Can't you say, for example, it's actually subjective to a certain extent. But unemployed means doesn't have anything, right?
Yeah.
He's not doing anything. Self-employed means he has something actually, some income level method. But it is not, it's not a fixed thing, right? It's not stable, right? But employed means, and usually we say employed, that's again a different thing, right? Self-employed is also employed, right?
Yeah.
So in that sense it is, yeah, in that sense, because these, how to separate these things. If you say this is permanently employed, that is a different thing, for example. Self-employed may not be permanently, it may be time to time. If you had, for example, permanently employed, probably it can be considered as ordinal. At the moment, probably it is nominal. Right? So you have to be careful about these things. You have to check further how these things are defined and so on. Right? So even, for example, even if a question in a questionnaire, if you ask employment status and then give these three choices only, somebody might find out which group am I belong to, right? Because if he's employed, he's employed already. So that is a weakness in that case. So that's you have to be very careful in wording in a question. Temperature of a patient's body measured in centigrade temperature.
Qualitative, continuous.
Quantitative.
Quantitative.
Continuous, yeah. Because temperature can be any value, even though probably we record it at a certain accuracy. It can take any value, therefore it's continuous. Job performance rating: excellent, good, average, poor.
Qualitative, ordinary.
Qualitative, ordinary. Yes. Study hours per week.
Quantitative, continuous.
Yeah, that again depends on how you ask the question. And study hours, if you ask, if your question says number of hours to the nearest hour, for example, then it is discrete. If you specifically say the nearest hour, so it has to be then 0, 1, 2, 3 and so on. But if you just say work hours, then it can be decimal number also, right? Up to certain, you can measure up to certain accuracy only. In that case, it is continuous. So depending on how you frame your question, depends on the type of the possible data. Soil type: clay, loam, sandy, etc.
Qualitative.
Qualitative, nominal. Yeah. Distance traveled by a bus in a day in kilometers. Distance traveled.
Quantitative, again, depends on the question.
Yeah. In kilometers, it can be decimal numbers, so it can be anything, right? But we record it up to certain decimal numbers, but the actual distance, even in kilometers, it can be anything in kilometers, right? So therefore, it is generally, according to the way it is mentioned here, it is a quantitative continuous one, right? If you say distance traveled by a bus to the nearest kilometer, then it is a discrete one. If you say nearest kilometer, then it is a discrete. Number of assignments submitted. Quantitative discrete.
Can be continuous sometimes.
How?
Submit half of the
the number of assignments, no? Number of assignments, not the number of questions. So that is one assignment. Maybe it is not complete. That's a different thing. But the number of assignments is discrete. One assignment. You may have done only part of that. That's a different thing. But it's one assignment. Right. Final exam class. First, second, that means grade, right?
Yeah.
First, second upper, second lower pass. Qualitative, ordinary. Field of study: science, arts, commerce. So, qualitative, nominal. Timetable to finish a 100-meter race in seconds.
Quantitative, continuous.
Continuous, yeah, quantitative, continuous. Even if measured in seconds, it can be decimals. Right? It's not asking to the nearest second or something. In that case, it will be discrete. But here, we are talking about the actual value. So quickly go to number of books in a library.
Qualitative.
Quantitative, discrete. Machine operating condition, on, off, or idle. Qualitative, nominal, right? Daily water consumption of a household in liters.
Quantitative.
Quantitative, continuous. Air quality index, good, moderate, unhealthy, etc.
Qualitative. Ordinary.
Yeah, you can put it as ordinary, right? Unhealthy is the lowest level and the moderate is higher. Good may be better, right? Type of cooking fuel, electricity, gas, firewood, etc.
Qualitative.
Qualitative, nominal. Number of goals scored in a football match.
Quantitative. Discrete.
Temperature range category. Temperature range category less than 30, medium, that means between these two, and then high above 60. Those are three categories. Qualitative,
Ordinary.
ordinary. Yes. So it's not that difficult. Okay, so now, therefore, now we can actually go back and look at this definition of a histogram. So histogram is a graphical display of the distribution of a quantitative variable, mainly when the variable is continuous. Right? So we use this as a graphical display of the distribution. Right? Now, when you collect the data for a quantitative variable which is continuous, then we have different numbers. Definitely, because it's numerical, we have numbers. But some numbers may be in the data set occurring less number of times. Maybe some numbers are occurring more number of times, right? More often. Right? So therefore, for each number, for each possible value, there is the number of times that particular value occurred. That is called the frequency. Right? So for different numbers, this frequency is different. Maybe one number is occurring 10 times, another number is occurring 15 times, another number is occurring 35 times. Right? Some numbers are not occurring at all, it's 0 times and so on. So the number of times each possible value is occurring in the, or each, maybe the values in a given interval are occurring, are different. So therefore we say the possible values are distributed in a range according to some distribution, frequency distribution, right? Different frequencies. The possible frequencies are distributed in a set of two values. So that's what I mean by the distribution. So this is a graphical display of showing that distribution. Right? For a quantitative and continuous variable, mainly we use in that situations, but sometimes we use histogram for discrete variables also. If the set of possible values is possible values are very close together, like as I mentioned, the proportion of something in a very large sample. In that case, when you are calculating the proportion, you are dividing by a large number, and therefore the possible values are going to be very close to each other. So even though theoretically that variable is discrete, sometimes we consider it approximately as a continuous variable. In that kind of situations also, we can use histogram to show the distributions as a graph. So, these words actually I have already mentioned the frequency, but there are several other words coming with that also. When you want to draw the histogram, we will need these words. You already know these ones in general English, but let me go through. As I mentioned, frequency of an item or unit value is the number of times that particular value is occurring in the data set. That's what we mean the frequency. The count of how many times a particular item happens in the data set. Right? So some number may have occurred 10 times, so that the frequency of that number is in that case 10. Right? The relative frequency is that frequency divided by the total number of observations. Right? If some number has occurred 10 times in a list of 100 items, then the relative frequency is equal to 10. Relative frequency is equal to 10 divided by 100. So actually relative frequency is the same as the proportion. Right? Proportion is the same. So these two words are the same. Right? Proportion is another term for relative frequency. So once you multiply the relative frequency by 100, then you get the percentage. Percentage is out of 100, how many, what is the proportion. Right? So these words are important when you are talking about histogram and other things, particularly the distribution. So let me start with this graphical displays. Like even though we are going to talk later on about the histogram, I will look at first of all a situation probably histogram is not suitable. That is, if you have a discrete variable where the set of possible values are not that close to each other, like this. A product is sold to wholesale dealers in batches of 100 units. Let X denote the number of defective items in a 100 unit batch. Right? So each batch is 100 units. So if you look at randomly select one batch and find out the population of interest is set of all batches, right? So suppose you are producing some item and you are selling them in hundreds, right? So one batch is 100. We select a sample of 25 such batches, and the sampling unit is then one batch, that is 100 units. For each sample batch, we count the number of defectives. So here we are looking at a variable, the number of defectives in a batch. That is the variable, number of defectives in a batch. So what are the possible values for that variable? Theoretically, if you look at number of possible values for the number of defectives in a batch, can be 0, can be 1, can be 2, up to even 100. Theoretically it is possible. But usually when you sell something, those large values are very, very unlikely to happen, but theoretically there is a possibility. Right? So when they practically observed 25 batches, these are the numbers they observed. Right? In the first batch there were no defectives, in the second batch there was only one defective out of 100, in the third there were 0 defectives and so on. So these are 25 numbers here. So you can see that some numbers are occurring more with a high frequency, some numbers are occurring with less frequency, some possible numbers are not occurring at all. Right? So therefore we can talk about the distribution of values. The possible values are from 0 to 100, but different these values have different frequencies here in the data set. So how do we show this? One way is to prepare a table like this. This is called frequency table. Right? So the possible values are, I say x1, x2, x3 are the unique possible values. Right? So 0 is a possibility, 1 is a possibility, 2 is a possibility, and so on. 5 is a possibility, but 5 has not been observed here. Therefore, we don't have to put 0 frequency there. Right? We are including only up to only the values which have more than 0 frequency. So frequencies here we have 9 zeros, 7 ones, 5 twos, 3 threes and 1 fours in the data set. The total number is 25. Right? So if you divide these numbers frequencies by the sample size, we have 25 samples. So therefore divide by 25, these are the values, relative frequencies, and sum of the relative frequencies is equal to 1. Right? They have to add up to 1. And if you multiply the relative frequency by 100, these are the percentages, and the sum of the percentages have to be equal to 100. Right? So if you consider these two pairs, right, 0 and 9, 1 and 7, 2 and 5, 3 and 3, 4 and 1. That is considered that list of pairs is what we call the frequency distribution. O as a table, if you consider only this part, that is the frequency table, frequency distribution, right? If you consider this row and this row, that gives you the relative frequency distribution. If you consider X and a row and this row, then it gives you the percentage distribution. So distribution comes like that. Then what kind of graph can we use to show the frequency distribution or the relative frequency distribution or the percentage distribution? Some people use bar chart. So in that case, they will draw a bar. In this case, this will be, for example, if you are looking at the frequency distribution, this can be your x. So you have, for example, 0, 1, 2, 3, 4. So you, some people draw this like the frequency. So one might draw like a bar on top of 0 and height has to be 9, right, like this. And then 7, so that is going to be like this. So like that they will draw a bar chart. That's okay, that's acceptable. But what I have drawn is not really a bar chart, it's a kind of a line chart. Instead of a bar with some width, I represent them with some lines here. So if you have frequency on this axis, then it's called the frequency distribution. If you have the relative frequency, then you can call it the relative frequency distribution. If you have the percentage, then percentage distribution. So if your objective is, for example, to see, for example, the shape of this distribution, right? Where is what number has the highest frequency, which number has the lowest frequency, whether it is increasing and decreasing, or whether the frequencies are decreasing, like that. If you want to look at the characteristics of that, any of this is okay. Any of this is okay. But if you want to, for example, compare the distribution of say height in one population with this distribution of height in another population, this is not that suitable. Frequency distribution is not that suitable. Why?
Can't compare the time, put the data to the same 2 days at the same graph.
I didn't understand.
You can't draw the.
You mean you can draw on the same graph?
Yeah.
No, you can, if you want, for example, you can draw frequency distribution of taken from of the sample taken from one population here, and then you can draw again frequency distribution of the sample, because you don't observe the whole population. You take a sample and then based on the sample you draw the frequency distribution. So you can draw here, then you can compare. What will be the problem with that? What are the possible problems if you look at the two frequency distributions to compare?
Assuming the value that you find.
Assuming what value?
Like the same data has to be, some data must be higher, like it depends on the
Yeah,
eye, you know.
I think what you mean is like you say, for example, when you take two samples from two populations, one thing is that you don't have to have the same sample size. If the sample sizes are different, frequency will be proportional to the sample size. So if suppose you have 50 observations from one population and 25 observations in one population, then the frequencies cannot be compared because the total sample size is not the same. So even if in that scenario, when you have two different sample sizes, still you can compare if you have relative frequency, because in this case relative frequency relative to the sample size. Right? So if you have one relative frequency here in another relative frequency side by side, you can compare, right? Because both are now relative to the total, and the sum of the relative frequencies is always 1. But here if you have frequency distribution, some of the frequencies will be 15 and one, the other one 25, for example, frequencies. So that is an important thing. Frequency distribution is therefore we don't usually that much, especially even if you are considering one variable only, still people don't usually use frequency distribution. They use either relative frequency distribution or percentage distribution, right? Because both can be used to compare also. And percentage distribution is even more, I think, practically meaningful and useful, because many people don't know what the relative frequency means. But almost everybody knows what the percentage is. So therefore, in that sense, probably percentage histogram will be more practically suitable. Even if you are considering a single variable, everybody knows what the percentage is. So percentage distribution gives you the whole idea. If you would compare it with some other, still percentage distribution is suitable. Right. That's what I have mentioned here. Any of the three can be generally used if you want to only visualize the shape of the distribution, but if you want to compare, probably percentage distribution is the best. Right. Now let us go to the histogram idea. Actually, as we mentioned, we use histogram mainly to see the shape of the distribution when the variable is continuous variable, numerical continuous. So let's look at an example. The following table shows the frequency distribution of marks of 200 students. Draw a suitable graph to get an idea about the distribution of marks. So you are given the frequency distribution. In this case, when you have actually a continuous variable, you don't usually have individual values. You don't look at the frequency of individual values, because usually for a continuous variable there are a large number of possible values. If you look at the data set, there are a large number of unique values, different unique values. So in that case, you will have a very large table here giving each frequency separately. So therefore, usually what we do is we group them in some meaningful way and then find out how many observations within that particular group and how many within the other group and so on. So this is called grouped frequency distribution, grouped. But the way that people group, you can see that when you look at books and papers and so on, you will see different ways people have used to group them. This is one way people use. In this case, these are called any method. Actually, these are called class intervals. But the way the class intervals are prepared are different in different presentations. Here you can see that, for example, 0, 10 and 10 to 12, 20 to 30. So if you just look at this one, there can be a confusion as to, for example, suppose the marks of some student was 10, right? To which interval that person belonging to is a question, right? Whether he is belonging to this one or this one. So if therefore it's better actually if somebody gives you this kind of intervals, it's better to clarify that. Right? So I have clarified that class intervals include left limits but not the right limits. So therefore somebody's marks was 10, that person would be included here, not here. Right? Now the marks, right? You know, when you get the marks, usually teachers give you integers, right? Very rarely they give you decimals. Right? But you can consider the actual marks as anything between 0 and 100. For example, probably what you get is a discretized version of that. Right? It's like measuring something up to a certain accuracy. Right? So therefore the variable itself is continuous. Right? So therefore, any mark, any actual mark up to 10 but less than 10 should be included here. And the other ones will be included here. So of course, if the marks are recorded as integers, anything up to 9 will be here, 10 will go here. Right? Anything up to 19 will be here, then 20 will be the other ones. So if you are given a frequency distribution like this, how would you draw the graph? I think many people will be drawing like this, right? If they are considering frequency, then they can show the frequency distribution. You can convert the same to percentages. Then the percentage distribution will be like this. Both look the same, shape is the same. Right? Now in this case we saw that all the classes have the same width. All the classes have the same width. Right? Width is 10. All the classes have the same width. So when you have the same width, actually, you can, if you want, you can show the frequency or the percentage. In this case, the height of the bars will be equal to the frequency in each class. In this case, the percentage will be shown by the height of the bars. This is what many people do in that case. But this is not actually a histogram in one sense. Can you see any problem here with this kind of graph? Let's consider, for example, percentage. No, let's consider frequency because we already have frequencies here. Let's consider Let's consider this graph. Can you tell me any problem that one might have when you are interpreting or using this thing for something else? Suppose you are not given the frequency distribution itself. Numbers are not given. Suppose you are given only this picture. And you have to use it for some other analysis. Any problem here?
You can see the exact frequency.
Yeah, you cannot see exact frequency, but still if I draw some scale here, you can still read it to a certain extent. That may not be a very big problem. But still, yeah, you can improve it a little bit. Okay, to help you, let me ask you, what will be the frequency between 40 to 45? 40 to 45 is here. So suppose this is 30. Forty to 50 is 30. So what will be the frequency from 40 to 45? You don't know, but can you guess it from this one table? Can you, if you use the table, because this table, for example, in the frequency table, this height is equal to frequency, right? So that means here, if you interpret the interval 40 to 50, there are 30 people in this group. If you use the same logic here, if you look at 40 to 45, right, still height is 30. If you use the same logic. But that is not correct, right? You cannot have 40 to 45, 30 and then the other one also the same number. So that will cause a problem here in the interpretation if somebody is more careful about it, right? So how would you avoid that problem in that case? How can you avoid having that wrong interpretation?
So frequency from the area, not from the height.
That's right. So what you have to do is you have to show the whatever the frequency by the area, not by the height. Right? So you have to get the height according to that. You have to adjust the height so that the area will be proportional to the frequency. So if you prepare that kind of graph, that is what you call the histogram. Histogram is something like bar chart, of course not a bar chart, because in a bar chart, usually the bars are separated. There are gaps definitely within a bar chart, especially to show the discreteness. Right? We usually use bar chart or qualitative variables. So in that case, we have categories. Categories are completely separated. So in order to show the separateness of these categories, usually we leave gaps between the bars. Even in the previous situation, if you are looking at a discrete variable, still sometimes people use bar chart, right? Then there is some discreteness, gaps between the possible values. In order to show that, people have to leave gaps between bars or the lines. Right? But here, the possible values don't have any gaps. So you have to show the continuity also. Right? So therefore, one main difference between the bar chart and the histogram is, in the bar chart you definitely have to have gaps to show the discreteness or the separateness. In a continuous, you have to show the continuity by not leaving gaps between the bars. There are no gaps between bars in a histogram. The second thing is that in a histogram, in the bar chart, the height of the bar shows the frequency or the percentage or the relative frequency. But in a histogram, if you use that idea, then the interpretation will be wrong in a certain sense. Therefore, in a histogram, the area of a bar, area of a rectangle should be proportional to the frequency or the percentage or the relative frequency, depending on whether you are looking at the frequency histogram or the percentage histogram. But as far as if you want to just compare the or if you want to find out which interval has the highest frequency or highest this thing in the given intervals, right? Not breaking into separate parts, then this is fine. But better thing is actually to draw, whenever you have a continuous variable, better thing is to draw a histogram with those two properties: continuous, no gaps between bars, and the area should be proportional, not exactly equal necessarily, but at least proportional to the frequencies or the percentages or the relative frequencies. So in order to show that, I have looked at the same data, but separated into classes in different ways. Right? For example, if you want to look at the grade distribution, grades are given for different ranges, not the same equal intervals. Right? So suppose you are given the frequency distribution like this, 0 to 24, right? Usually that may be the grade maybe A, B, C, D, E, F, for example. Right? So 25 to 39 will be E and so on. Right? If the grades are given like that, one might give you this frequency table. So if you have this kind of frequency table, these class intervals are not the same as the previous ones. Here they are not the same here, they are not overlapping. So how would you draw the suitable picture here? You can draw again the frequency distribution or the percentage distribution. If you directly draw the picture showing, for example, the percentage as the height, this will be the picture that you get. So for example, here the first one has 6% and then 14% and so on. So if we just draw the bars over the interval, corresponding interval, so that the height is equal to the percentage, this is the picture that you are going to get. So clearly this is not the correct one, because for example again, this tells you that between 70 to 100, there are 17.5% of the students, but it gives you the same idea again, 70 to 80 also 17.5 and so on. That's going to be completely wrong. Right? So definitely this is wrong. It's not a histogram or any other meaningful graph. It's not a histogram because of two reasons here. Because there are gaps here. Right? Histograms should not have gaps. And the areas are not proportional to the percentages. So both reasons is not a histogram. Right. So if you want to draw a histogram, how do you do that? Now, what will you do? You have this class intervals in the table. You have to have class intervals. Out of these, now you have to create some class intervals without any gap. You have to remove the gap first of all. Right? What is a meaningful way to remove the gap here?
Class width of 5.
Class width of 5. But then you will not be able to get the grade distribution, right? So suppose you want to look at the grade distribution, you have the grades are distributed. If you change these things, then the grades will disappear. Grades, you cannot see the grades.
0.5 and decrease 0.5 from.
Yeah, actually that is the best thing you can do. Right? You know that this 0 definitely means 0, right? Because you don't give negative values. 0 means 0. But 24 means what actually? Because this is a continuous variable. Any actual mark up to 24.5, right? Not including 25.5, 24.5 will be recorded as 25. But anything less than 24.5 will be included in this interval, right? So therefore you can write this thing as 0 included and then 24.5 excluded, open as that. And then 24.5 will be included here. Right? So 24.5 closed interval on that side and then 39.5 open interval the other side. Like that, if you make this thing like that, then there will be no gaps. But the same meaning will be there. Meaning is not going to change. The same meaning will be there. Therefore, these frequencies can be used as they are. We don't have to change the frequencies. So that's what we usually do. In that kind of situation, we recreate our class intervals like this. Now, some people always mechanically add 0.5 here, subtract 0.5 here. We don't have to be mechanical, we can be meaningful, right? Because we know we are not going to get negative values, so we are not going to get marks over 100, right? So therefore 100 means 100, so you can just put 100 close point here. And then here 0 close point here. You don't have to take it minus point, negative 0.5 and then 100.05. We don't have to do that. That's not going to be meaningful. So we have to be always meaningful what we are doing. So therefore we can do something like this. So still the percentages will be the same, but now we have to find out the heights of our bars so that the area will be equal to percentage. Area of a bar should be equal to the percentage. So in order to do that, we have to divide the percentage by the width of the interval. So here the width is 24.5. When you divide this by this is what you get. So that gives you actually the percentage per mark. Percentage per 1 mark. Right? So that's kind of a density. Percentage per or something per unit. It's kind of a density. So therefore we can call it, if you want, percentage density. Right? The density means here per unit mark. So like that you can calculate the percentage density, and then percentage density will be the height of the bars over these intervals. So when you calculate, of course, the percentage, when you divide these things, we have to record it up to a certain decimal. You cannot write down 25 numbers, so you have to round them. When you round them, sometimes the total area, theoretically the total area has to be equal to 100, the total area. But when you multiply this by this, and then if you calculate not the total density, total area has to be 100. That means here the area will be this equal to this times this, area will be this times this, and so on. Right? But even though the percentages add up to 100 here, the areas may not be add up to 100 because of the rounding operators, but it will be close to 100. It's not going to be a big deal most of the times. So this is the distribution that you will get by doing that. So this is what you mean by a histogram. It has all the properties that it should have. Right? All the bars are touching each other without any gap, and the areas of the bars are in this case equal to the percentage. But sometimes if you want to compare two things, you can have to be proportional. Right. So that's what the histogram is. That's one example, and I have given another example from the book. I put my time to go off at 10 o'clock. I thought I would change it, stop in 1 hour and then take a break. But anyway, now I am stopping 1.5 hours.
So I stop the video.
No, we'll go another 5 or 6 minutes. Right. So this is an example taken from the book. So here again, the intervals are given with a common value, and it says class intervals include the left endpoint. So if you have common endpoints like this, you must always mention how it is how it has to be. In some cases, maybe they are including the right endpoint, not the left endpoint. So whatever you have to mention usually, otherwise the reader doesn't know what it really means. Right? So when you are constructing histogram, you have to see that the width are not the same here. Some have with 1,000, some have more than 1,000, and so on. So therefore you have to actually calculate the density first of all. So the density will be then income per $1,000, because here the units in the graph going to be in thousands of dollars. So the density will be in that case. So this graph is not a suitable graph. It just shows the percentage. Right? That's not a correct graph. Even though no gaps here, still this is a wrong graph because it's showing the percentage. The right graph is like this. You have to get it the percentage density first of all, and then use this as the heights. So then the picture will be like this. Okay, so we'll take a break now.